Okay guys, here we go. Last chapter for the semester, chapter 11. Now in chapter 10, we were looking at the gas laws and looking at the physical properties of substances in the gas phase. So what do all gases have in common? Here in chapter 11, we're going to look at solids and liquids as well as gases. We're going to look at phase changes and what controls phase changes, and start to understand a little bit more about the physical properties of substances and then how that's going to affect their ability to chemically interact. So let's remind ourselves about solids, liquids, and gases. If something is a solid, we say that it's rigid, it has many surfaces, it has a set shape and a set volume, and it's not compressible. That means on the atomic level that the particles, be they atoms or molecules, are close together. The only motion is vibrational motion. Attractions are stronger than forces of collisions, so they stick together, so attractions dominate. In the liquid phase, there's no set shape. There's a set volume. You have one surface. The liquid's going to fill the container up to the volume it's going to occupy. It's considered a fluid and it's not compressible. So the particles are still close together, but maybe not quite as close together as they are in the solid phase. The particles move past each other. Attraction and forces of collision are on par with each other. So neither one truly dominates. They just kind of hold together and they move past each other. Okay? And then lastly, gases, which we spent all last chapter looking at. No set shape or volume. It's a fluid, and it is compressible. Notice a liquid is not compressible, a gas is. The particles are far apart, and there's lots and lots and lots and lots of movement. Forces of collision dominate here. When two particles collide into each other, the force they apply during the collision is much greater than the attractive forces between the particles, so they don't stick, they just bounce off each other. Okay? So solids, gases, and liquids. Whether a substance is a solid, gas, or a liquid depends on then that interplay between intermolecular attractions, the attractive forces between particles. These are usually weaker than bonding forces. With ionic compounds, whether they're a solid, liquid, and gas depends on the strength of the intramolecular forces. Okay? And the collision forces due to the motion of the particles, be that translational motion or vibrational motion, which tries to push the particles apart. So when the particles collide with each other, they apply a force on each other, which essentially says move away from me or move out of my way. The faster they're moving, the harder they collide, the more force they apply to each other, the more they want to move apart. Okay, so what we have is a battle going on between attractive forces and collision forces. Whichever one's stronger dominates the outcome. The attractions between particles, okay, is going to be structure dependent, and it doesn't change. The attractive force between two particles is a constant. But as temperature changes, the kinetic energy of the particles change, which means that they're going to be moving at faster speeds, which means that their force of collision changes. So if the temperature goes up, the average kinetic energy goes up. That means the average speed of the particles goes up. That means the average force of collision goes up. So one of the ways to change the phase of the substance is to add or remove energy. If we add energy, okay, to a solid by way of heat, the solid would melt into a liquid. So notice that in this image of the solid, okay, there's a nice regular pattern of the atoms. They're all clinging together. They have a specific shape no matter what container they're in. When you add heat in and you melt, Now we get a little bit more disarray in the particle arrangement. Notice that now it's occupying a volume at the bottom of the container. Okay, it's got an upper surface. And in the gas, we had to put a lid on it or it would escape. Notice the particles are very far apart and they're rapidly moving. So we add energy in. Notice it also says reduce pressure. We increase, well, we go from solid to liquid to gas. If we cool, we go from gas to liquid to solid. Now, solids have low potential energy, which means the particles are close together and are interacting strongly. And for that substance, you would also consider it to have a low kinetic energy, okay? Because the particles aren't moving a whole lot. In liquids, they have a potential energy that's a little bit greater than the solids because the particles are a little bit further apart. Okay, they're not as close together as they used to be. And for a given substance, it's going to have more kinetic energy. If I have something in the solid phase and the liquid phase at the same temperature, like at the melting point, they're going to have the same kinetic energy because they have the same temperature. But the liquid would have more potential energy. Gases have the most potential energy that's much higher than for solids or liquids because the particles are very far apart. And gases are going to have a higher kinetic energy for a given substance. Now, just like looking at solids and liquids at the same temperature, if I looked at the liquid phase and the gas phase of a substance at the same temperature, like at the boiling point, they're going to have the same kinetic energy, but they're going to have different potential energies. So, going from a solid to a liquid to a gas requires energy be added. Moving from a gas to a liquid to a solid requires energy to be removed. So let's label our phase changes. A phase change is change between the phases. Freezing is a liquid to a solid. It requires that we remove energy. It's exothermic from the point of view of the substance. Melting or fusion is solid going to liquid. It requires energy to be added into the system. It's endothermic. Melting and freezing are opposite processes. Notice how one you removed and one you added. Vaporization is liquid to gas. It requires energy be added in. Condensation is gas to liquid. Energy is removed. Now, those four you're familiar with. The next two are ones you may not have seen before. Sublimation and deposition. Sublimation is a solid to a gas and it requires energy be added to the system. Deposition is gas to solid and it requires energy to be removed from the system. Dry ice is called dry ice because under normal atmospheric conditions, it sublimes. It goes straight from the solid to the gas without ever going through a liquid phase. Okay? Different substances have different temperatures of phase transition. This is due to the differences in the attractions between the particles, the molecules, the ions, or the atoms. The stronger the attractions between the particles, the more they want to stick together, which means they're going to have higher melting points, they're going to have higher boiling points, okay? It's going to need more energy to overcome those attractions to do that phase change. So if we were to look at carbon dioxide, water, and glucose, CO2, H2O, and C6H12O6, and we were to look at their states at room temperature. CO2 is a gas at room temperature, water is a liquid at room temperature, and glucose is a solid at room temperature. So knowing that they're all at the same temperature, I know they all have the same average kinetic energy, which means they're all experiencing the same kind of collision forces. But carbon dioxide is a gas, which means that it has to have the weakest attractive forces between it. And the one with the strongest has to be the glucose because it's the one that's a solid at room temperature. Its attractive forces are much, much stronger than its collision forces for the particle. Okay? Now, let's start talking about what these attractive forces are. These attractive forces are called intermolecular forces. Intermolecular forces, the attractive forces that account for attractions between molecules and ions, and non-covalently bonded atoms, things like neon or xenon or argon. If we were to look at solid chlorine, okay, chlorine is made up of a diatomic molecule, Cl2. We would observe two different distances between adjacent chlorines. The shorter distance is the bond length due to the covalent bond between the two chlorine atoms. The longer distance is called a van der Waals distance. Okay? The van der Waals distance is referring to the distance between two chlorine atoms that are involved in an intermolecular interaction, not a bonding force. Okay? So there's two differences. Now, we've got a list of intermolecular forces. Okay, and I'm going to start off by looking at the intermolecular forces that we find in pure substances and mixtures. And then we'll look at the intermolecular forces only seen in mixtures. Okay? Our first intermolecular force is dipole-dipole. A dipole-dipole is an attraction between polar molecules. It's most important for small, highly polar molecules. Okay? So a dipole-dipole is an attraction between molecules that are polar. Now, let's look here. Here is the structural formula for dimethyl ether. Okay, it's not a full Lewis dot structure because, not all of those are drawn out and they're not showing the lone pairs on the oxygens, but this is a structural formula. Okay, if we look at a space-filling model, there's the oxygen, there's the central carbon, the two side carbons, the whites are hydrogens, and it's a polar molecule. Because if you look at the central carbon here, there's three groups around the central carbon, one of them oxygen, two are methane groups. So not all three groups around the central atom are the same. That's polar. Oxygen is going to be the slightly negative end of the molecule, and centered over here on the methane side, okay, it kind of in between those two methane groups, that's the center of positive charge. So these molecules are pretty small and they're polar. So because they're small and polar, we've got a dipole-dipole interaction. Okay? Here's an electrostatic molecule where things are red, that's high electron density. Where things are blue, that's low electron density. High electron density, slightly negative. Blue, low electron density, slightly positive. Okay? All right. Now, here we're showing propane dimethyl ether, ethylene, ethylaldehyde, and acetonitrile. Now, if we look down here at the bottom, dipole moment is referring to how polar the molecule is. The more polar the molecule, the larger the dipole moment. Notice that, and that means that there's going to be stronger attractions between the particles. Notice that as the dipole moment increases, the boiling point increases. The stronger their attractions, the more they hold together, the harder it is to get them to jump into the gas phase. Our second type of intermolecular force is hydrogen bonding. Now, Hydrogen bonding is the attraction of a hydrogen that's bonded to an oxygen, nitrogen, or fluorine on one molecule for a lone pair of electrons on a nitrogen, oxygen, or fluorine of another molecule. Okay? This is a very site-specific intermolecular force and is very important biologically speaking. It helps in the folding of proteins. It's what locks the two chains and the double helix together. Okay? So, to have hydrogen bonding, you already have to have a polar molecule. So when we're looking for intermolecular forces, we want to look first to see if it's polar. And if it's polar, then we want to see if we have a hydrogen bonded to an oxygen, nitrogen, or fluorine. And if there are lone pairs of electrons on that molecule. So let's start by looking here at HF. Okay? Fluorine atom, hydrogen atom. Now let me draw an HF here, draw its Lewis dot structure. Okay? So here's HF. Now what I want you to notice, the electronegativity of fluorine is 4.0, hydrogen is 2.1. Okay? That means that this bond is very polar and the electrons are being pulled from the hydrogen to the fluorine. And notice that the fluorine has 3 lone pairs of electrons. Now, this has a difference in electronegativity of 1.9, which is a pretty good difference in electronegativity. It's still covalent, but boy, is it polar. All right, so it's a very polar molecule. Now, the fluorine end is our slightly negative end. The hydrogen is our slightly positive end. Okay, so I've got a dipole-dipole interaction going on. But on top of that, a lone pair of electrons here is attracted to the hydrogen, or you could say the hydrogen is attracted to that lone pair of electrons. They line up in a very specific way. Okay? There are 3 lone pairs here. It could come at it from this angle too. So between 2 HF molecules, there's a dipole-dipole interaction and there's a hydrogen bond. Now, the next pretty picture I've got here for you guys is the interaction between water molecules. Water is sometimes referred to as the king of hydrogen bonding. Okay? The red is the oxygen, the blues are the hydrogen. Look at this guy. He's got 2 lone pairs of oxygens that can hydrogen bond with hydrogens on other atoms. And it's got 2 hydrogens that can hydrogen bond with oxygens into other water molecules. So one water molecule gets involved in, or has the potential to be involved in 4 hydrogen bonds. It's also polar. So between water molecules, we see a dipole-dipole interaction and we see hydrogen bonding. Hydrogen bonding is what allows water molecules to interact with a variety of covalent compounds and help dissolve them up. All right. Now, one thing I want you to notice here, notice that the hydrogen-oxygen bond, quite short, they show those electron clouds fused together. Notice the distance between this lone pair of electrons and this hydrogen is quite a bit more than you see in the bond. Okay? In the true covalent bond. All right, now let's roll on down here. Now, here's a ethyl alcohol, drinking alcohol. Okay? This is a structural formula. Down at this end, we have an OH group. The OH group is what makes this an alcohol. Okay, on that oxygen, there are 2 lone pairs of electrons. This oxygen, there's 2 lone pairs of electrons. So this hydrogen can interact with that oxygen through a hydrogen bonding situation. Okay? So here we can see the hydrogen bond situation. We have a polar bond here. That's the negative end of the bond, that's the positive end of the bond. There's the hydrogen bond between this hydrogen and the lone pair of electrons on that oxygen. And again, that's just another way to draw it. Okay? It's a hydrogen bond. Now, if we look at this graph, I want you to notice there's a trend. If I look at CH4, SiH4, GeH4, SnH4, if we look at carbon, silicon, germanium, tin, they're all members of the same family, the carbon family. And I have the same formula as far as number of the first atom to number of the second atom, 1 to 4, 1 to 4, 1 to 4. Notice that boiling point goes up. And that's because silicon's larger than carbon, germanium's larger than silicon, tin's larger than germanium. We'll talk about why that happens in a minute. But generally speaking, usually as molecules get larger, their boiling point goes up. Okay? If we look here though with nitrogen and then, ammonia, NH3, and then PH3 and ASH3 and SbH3, okay? For the phosphorus, the arsenic compound, and the antimony compound, the trend holds, but notice the nitrogen's way out of line. We'd expect it to be down in here based on size. The reason that it's out of line is because the nitrogen has that lone pair of electrons, and it can hydrogen bond. It can create then hydrogen bonds between ammonia molecules. Same thing with HF. Okay? Notice HCl, HBr, HI, boiling point goes up, but HF is way out of line. Same thing with water. Water's way out of line because it can make so many hydrogen bonds. Okay? So there we go. We can see the effect on boiling point for hydrogen bonding. So let's scroll down. The third intermolecular force we're going to talk about is the London force. Yeah, that's better. The London force, also called the dispersion force, is an attraction between temporary dipoles formed when molecules temporarily polarize. London forces are dependent on the polarizability of a molecule. The larger the molecule or atom or ion, the more polarizable it is. The more elongated the molecule, the more polarizable it is. What does it mean to polarize? Well, it's when you take something that's got an even distribution of electrons and you cause the electron distribution to become lopsided. Okay? So let's look at some pretty pictures. Okay, so an instantaneous dipole would be if we think about having a spherical atom, and when they got close to each other, their electron clouds repel, and the molecules become egg-shaped. Well, the atom, in this case, the atom's electron cloud becomes egg-shaped. So it ends up with a slightly negative end and a slightly positive end, which causes other atoms around it to do the same thing. Okay? It's like when my mother walks into the room. I suck in my gut because she's always going to yell at me about being fat. All right? I can't hold it that way forever, wish I could, but it'll eventually go back to its original shape, especially if they move further apart. Let me show you some other pictures here. Ah! Whoa, come back, come back. There. Okay, so you can think about the particles starting out as spherical. They get that egg shape with a slightly negative and a slightly positive end, and then when they're in that egg shape, they're attracted to each other. Okay? The London or dispersion force is the most common intermolecular force at play. All attractions between particles involve some kind of London interaction. Okay? So the three interactions we've talked about so far are dipole-dipole, hydrogen bonding, and the London force. Everything has a London force or dispersion interaction. To have dipole-dipole, you have to have a polar molecule, one that has a permanent lopsidedness to its electron distribution. And to have hydrogen bonding, you need to have a hydrogen bonded to an oxygen, nitrogen, or fluorine that has lone pairs on it. All right. Now, to kind of reinforce things, okay, let's look at helium, neon, argon, krypton, xenon. All of these are noble gases. They start out as nice spherical atoms when it comes to their electron clouds. You can notice as they get larger, okay, their boiling point goes up. And the reason their boiling point goes up is because since you have a larger electron cloud, it's easier to get it into that egg shape, and you can move, you can elongate the electron cloud a bit more. So larger, more London force. Now here we have N-pentane and neopentane. Don't worry about the name so much. They are the same formula molecule. They contain the same number of carbons, 5, the same number of hydrogens, 12. Okay? They have identical molar masses, and that's why. But notice that they have wildly different boiling points. Okay, the boiling point of N-pentane is 36.1 degrees C. The boiling point of neopentane is 9.5 degrees C. The difference is the fact that N-pentane is elongated in structure, neopentane is spherical in structure. There's a central carbon and the 4 carbons on that one with the hydrogens on the outside. So structure, the elongation of the structure leads to larger London force, which leads to a higher boiling point. Okay? Book talks about the fact that if we have a longer molecule, there can be more points of contact, larger areas of interaction, which can lead to more polarity. I also like to think about it as the fact that the molecule is just better able to spread out its electrons. Now, here's the boiling point for N-pentane, N-hexane, N-heptane, N-octane, N-nonane. They're getting longer. Notice that as they get longer, okay, they have a higher boiling point because I've got more ability to spread out the electron cloud. Okay, we are now ready to start looking at the intermolecular forces that we only see in mixtures. London force, dipole-dipole, hydrogen bonding, we can see between pure substances, between like molecules, and we can see in mixtures between unlike molecules. The 3 intermolecular forces we're going to see right now are only seen in mixtures. The first one is ion dipole. It's the attraction between an ion and a polar molecule. This is what we see between water and the ions in something like sodium chloride or sodium nitrate. So any salt that dissolves up in water does so because of an ion dipole interaction. Okay? Now, the positively charged end of the polar water molecule, okay, is attracted to a negative ion, and the negatively charged end of the water molecule is going to be attracted to a positive ion. So notice the sodium here is surrounded by 6 waters with the oxygens pointing in. We've got the ion dipole interaction. The chlorine, which is negatively charged, the chloride ion, is surrounded by 6 water molecules with the hydrogen pointing in toward it. Okay? If the interaction that they can have with this dipole ion interaction is about as good as the bond strength, then the ionic compound is going to dissolve up in water. But if the ionic bond is really strong, not going to. Next is the ion-induced dipole. This is an attraction between an ion and a nonpolar molecule. The classic example of this is the iron 2+ in hemoglobin for oxygen. Hemoglobin is called hemoglobin. The heme comes from iron. Okay? So if we look at this interaction, there's a heme. This is a heme molecule. It's got in the middle an iron 2+. Okay? And it's in some coordinate covalent bonds. It sits in the middle of this kind of ring structure. And the oxygen is a nonpolar molecule, but the iron is so polar that it polarizes the oxygen and the oxygen sticks. Now, you don't want this to be a very strong interaction, not super strong, because when the red blood cell gets out to the cells, you want to be able to liberate the oxygen. If the interaction was too strong, it wouldn't release. That's why something like carbon monoxide poisoning happens. The carbon monoxide molecule is polar. When it comes up close to the ion, the iron 2+, it interacts through a dipole ion interaction and it sticks better. Okay? So the carbon monoxide locks up the irons in your heme components. So if you look at a hemoglobin, okay, it's made up of 4 units, 2 A chains, 2 B chains, and in the middle of each A chain and each alpha chain and each beta chain is a heme. Under normal atmospheric conditions here in Tuscaloosa, 3 of those 4 hemes would be loaded with oxygen when the red blood cells leave the lungs. Okay, we don't load usually all 3. If you live in Denver, it only loads 2 of the 3. People who live in Denver have a higher red blood cell count than people that live in Tuscaloosa. Now, our third one is our dipole-induced dipole attraction. It's an attraction between a polar molecule and a nonpolar molecule. This is the interaction that's at play for oxygen to dissolve up in water, nitrogen to dissolve up in water, carbon dioxide to dissolve up in water. I like that one because it makes soda fizzy. But those are the types of interactions that we see in a dipole-induced dipole. So it's an interaction between a polar molecule and a nonpolar molecule. Now I've included a table at this point, okay? Let's look at this table. The first 3 things you see here are the bond forces. The ionic bond, the covalent bond, and the metallic bond. And this is the bond energy. This is the range of energies to break that bond. How much energy does it take to break that interaction? Okay? All right. Now, those are called intramolecular forces or bonding forces. The non-bonding intermolecular forces then are our ion dipole, our hydrogen bonding, our dipole-dipole, ion-induced dipole, dipole-induced dipole, and the London force. Ion dipole, hydrogen bonding, and the dispersion or London force, those 3 can be seen in between like particles and between unlike particles. The ion-induced dipole, the dipole-induced dipole, and the ion dipole, hydrogen bonding dipole dispersion seen between like molecules and unlike molecules. Ion dipole, ion-induced dipole, dipole-induced dipole are only seen between two particles that are not the same. And I've got examples over there. Okay, so that's a nice kind of reference for you. Okay. Here's the one out of your textbook. It's not quite as big as the one that I gave you up above. I like the one up above better, but I wanted you to see it. Now, to determine what type of intermolecular force exists between like molecules or unlike particles, you need to know something about the 3D structure of the molecule. So all that stuff that we were looking with on Lewis dot structures to to electron group arrangement to molecular geometry, knowing something about what a molecule looks like in 3D, that's when this becomes important. Okay, so if I gave you CH4, we draw its Lewis dot structure, looks like this. Remember, all four groups around the central atom are the same. That means that this is a non-polar molecule. Since this guy is non-polar, then I know between like molecules, we see dispersion. And that's it. If I were to change that out and go CH3Cl, when I look at this, one group is different from the others. This is a polar molecule. So it's got a dispersion, because everything's got a dispersion, but because it's polar, I now have a dipole interaction between two of these molecules. Now, I have hydrogens here, but the hydrogens are bonded to a carbon. So this is not going to have any hydrogen bonding. So two molecules of CH3Cl have a dispersion interaction between them, and they're going to have a dipole-dipole interaction. Okay, if we were to look at ammonia, that's its common name. It would be nitrogen trihydride if we were using its systematic name. Okay, now I know that everything's got a dispersion. And I look at this, and I've got one lone pair and 3 bonds to hydrogen, so I know this is polar. Since it's polar, I know that I'm going to have dipole interactions between two ammonias. And now notice I have a hydrogen bonded to a nitrogen, which has a lone pair of electrons. So we can also have hydrogen bonding between these two identical molecules, two ammonias. Now look at this guy. Okay, this is called trimethylamine. You're going to walk with me. Trimethylamine. Okay? Now, we know that it's going to have a dispersion because all molecules get a dispersion interaction. And if we look at that central nitrogen, there are 3 methane groups, that's the CH3, and a lone pair. So this molecule is polar. And not be wildly polar, but it's polar. So it could have some kind of dipole interaction, okay? Now the question to you is, can this sucker hydrogen bond to another trimethylamine? Well, I have hydrogens and I have a lone pair of an electron on a nitrogen, but those hydrogens are bonded to a carbon. Since the hydrogen's bonded to a carbon, we get no hydrogen bonding. So this guy only has the dispersion and the dipole-dipole. Okay? All right. Now, you ought to then be able to look at the formula of this compound, do its Lewis dot structure. From its Lewis dot structure, you ought to be able to figure out if the molecule is polar or not. And if it is polar, can it also hydrogen bond? Okay? And that's a skill that you're going to build on and use, and we're going to use it a lot next semester. So I want to make sure that you're good at it. Okay. Now, let's start talking about some of the properties of things in the liquid phase and the solid phase that are going to reflect the strength of the intermolecular forces. We're going to talk surface tension, viscosity, capillary action, vapor pressure, boiling point, freezing point. Okay, so let's start off with surface tension. Now, surface tension is the energy needed to increase the surface area by a unit amount, such as joules per meter squared. Okay, now let's look at packing. If we look at particles in the center of a liquid, they're interacting with at least 6 other particles. Okay, they're being pulled by intermolecular interactions in all directions. Because of that, they're going to be a bit more space. If you're at the surface, you're pulled left, right, front, back, and down. There is no pull up. Because of that, the particles at the surface, okay, have a tendency to be pulled down. So the particles at the surface of a liquid are actually packed tighter than in the body of the liquid. Okay? So the stronger the intermolecular forces, okay, the more energy it's going to take to separate the particles at the surface. So in general, the stronger the intermolecular forces between particles, the stronger the surface tension is, or the larger the surface tension is. Think about little water bugs. Something you can try at home, since this is on video. Take a big bowl, fill it with water up pretty close to the top, take a paper clip, okay, and very carefully lay the paper clip on the surface. It'll sit there because of surface tension. If you then tap the side of the bowl so that you add some kinetic energy in, the paper clip will sink. You can do the same thing with a needle. Okay? Next up on our hit parade is viscosity. Viscosity is the resistance of a liquid to flow. The stronger the intermolecular forces, the higher the viscosity. Okay? Also, temperature plays a role. As temperature increases, because the particles have more energy on average, you also see viscosity go down. Think about heating up maple syrup or putting Karo syrup in the fridge, and you know how slow it pours when you get it out, and then if you warm it up, it pours better. Okay, now here's an example table. in pentane, in hexane, in heptane, in octane, in nonane. They're getting larger. They have longer molecules. So remember, longer molecules mean stronger dispersion forces. Okay? Notice as the dispersion forces get stronger, the viscosity goes up. Now, capillary action. It's the ability of a liquid to flow against gravity up a narrow tube. Capillary action depends on two forces: adhesive forces or adhesion and cohesive forces, cohesion. Adhesion is the interaction between the liquid and the walls of the container. Cohesion is the attraction between liquid molecules and liquid molecules. If adhesive forces are greater than cohesive forces, then the liquid gets drawn up a tube. So if the cohesive forces are stronger, then the liquid does not rise up the tube. So look here. Notice that as the tube gets narrower, the column rises higher. This is water interacting with glass. Glass is silicon dioxide, has lots of oxygens with lone pairs of electrons, and the water can hydrogen bond with it pretty well. So it can climb up. If you have the narrow tube, that limits the interaction between water molecules and ups the potential for interaction between water molecule and glass, and that helps it climb. Okay? Over here, I want you to see mercury in a glass tube. Notice the mercury gives us a convex meniscus. And that's because mercury doesn't have a very good interaction with glass. In fact, it doesn't want to interact with glass. It has a much, much stronger interaction with other mercuries. So it reduces it. Here's water in the same kind of test tube. It gets a down meniscus because the water has good interaction with glass and it wants to climb up. Now this is the reason you do things like wax your car. When you wax your car, you reduce the interactions between the water molecules and the paint, which has a lot of places to hydrogen bond. And when you coat it with wax, wax cannot hydrogen bond to water, and the water beads up. Strong cohesive interactions, poor adhesive interactions, and it rolls off. Okay, now let's start looking at phase transitions. Okay? In fact, this is probably a good place for me to stop and pick up here with the next one. So this has been about a 45-minute video. So we'll pick up with phase transitions next time.